Good morning, folks. Tutorials 10 through 15 are using the 3D Experiences FEA module to solve the same very basic structure analysis problem. Okay, instead of putting all of these different things in one video, which can become very long, I decided to break it up into six individual videos, and in each one of them, particular aspect of the modeling will be discussed. This one, I call it the obvious strategy, and the situation is as follows. We have a cantilever beam, but actually it's also supported on the right-hand side. It is, I should not call it cantilever, but anyway, it's this structure. And there is an internal hinge at the point B. That means there is no moment at this location. Concentrated force here and the moment, concentrated moment at this end. Now, I call this thing the obvious strategy because what I'm going to do is basically model AB as one line, proceed with that. Okay. The problem is coming from Hebler's structural analysis book, and the deflection, the theoretical deflection, the way I'm going to assess the validity of my model is that the analytical solution, which is done in the last 3 pages of this PowerPoint, is going to be 4.58. Okay, 4.58 should be inches, should be a displacement of the point B, and if I get that, means that I'm on the right track. Now, so here's my strategy, the obvious strategy. There's going to be one line, line AB, line BC, and the concentrated force is here, and the hinge is over there. Now notice that because I'm making this thing as one line, and I have to put a concentrated force somewhere in the middle, I really have to create a group, or as Abacus users call it, a set, and place that force, concentrated force, on that set. Okay, we already talked about these things in earlier videos, and now the internal hinge is going to be done at that location, and I'm going to be using the connector. I have to use a connector in 3D Experience / Abacus, which is can be any one of these. It can be a hinge, joint, or a cylinder, and I'll show you that regardless of which one you use, you get the exact same value for this displacement at the hinge. Okay. Now, my strategy is to create a line AB as a wireframe, a line BC again as a wireframe, but I'm not going to join these two because I want to create duplicate nodes at this location so that I can create a hinge, okay, or I can create an internal hinge basically. So I'm not going to join these two. Now, because I'm using wireframe, I don't even have to join individual lines, because this line AB, if I did the sketch and I try to do the problem, I will have to go back and join line AB. But because I'm doing it as a wireframe, that is not necessary. Also, so this side is going to be meshed and this side is going to be meshed, but they're going to be done separately. And I want to make sure that there are duplicate nodes at this location. In other words, make sure that this capture box is off. Because if the capture box is on within the tolerance that's specified here, if you expand this capture, these two nodes are going to be meshed. I don't want to do that. So make sure that when you mesh these things separately, this is not active. Okay. Now, because I'm using connectors, and connectors such as hinge, cylindrical, and joint do need a local coordinate system, because basically telling the software it's hinged about what direction. So what I need to do is when I get to, for example, create a hinge, I have to select an axis system as I've created here, and if the axis system X is in this direction, the way it's created, then obviously it's going to be hinging about the X axis, okay? If this X is accidentally on that horizontal line, or you decide to change it, then it's not going to even see it. Okay, so X like that, obviously the axis of the hinge is X, or X is going to be released, and it has to be in this direction, or in the other. But don't put it, for example, up or on the horizontal axis. Okay, so these are some information. This is some information from the source, and I've solved this thing analytically using the visual word principle and the calculation. In case you want to look at this, you can stop it and check it out. The calculation is roughly 4.58 down. Okay, so let's go ahead and do the problem. I go to because I don't need to join anything, I can do in part design or structure or generative shape design. So, okay, so I'll do it in generative shape. All right, so I'm going to create two lines. So line one, point and direction. The point I'm going to create 0, 0, 0. The direction is going to be Y, and it's 24 inches long. Okay, so that's my first line AB as you want. Then another line, again, point and direction. There is the point, direction is Y, and it is 15 inches. So not inches, sorry, feet, 15 feet. Good. Okay, so that's pretty much it. So while we are at it here, let me create an access system, which I'm going to be using later on. Okay, if I don't create this thing right now, I'll have to come back and do it anyways. Okay, uh, so let me create an access system, and I'm going to place it right at that location. Okay, that's where the hinge is going to be. And notice that X is pointing this way. You can change the direction of X by selecting different orientation. For example, if I select, for example, X-axis, I can put it on this line. I don't want to do that, but see, I don't want to do that. So no selection. Let me cancel that. Let's try it again. There. X is in this direction. Very good. If I didn't do this thing right now, I would have to come back and do that later. So let's go and apply material. So let me create a material here. Actually, this is the browser. Let me go create a material. So add. I'll call this thing internal hinge. Hinge. I'm not going to do this step in every one of these. Well, okay, I'll do that. Internal hinge. Okay, it's going to create it in the database, and I'm going to take this thing and apply it to that. Now we're going to put the values in it. So double click on the material. It's electromagnetic, structural, abacus multiphysics, mechanical, elasticity, and for Young's modulus, I put 29,000. I don't, yeah, 29,000 KSI. And for Poisson ratio, I put down 0.3. All right, good. So this is all done. Now we're going to go to the meshing module. So we go to structure model creation. Okay, that's fine. Empty FEM. And we click on the mesh, beam mesh. It's going to be 1 foot long elements. So there's going to be 24 of them here and 15 of them in the other one. And notice that this box is off. I don't need it. It doesn't matter right now, but for the next element, with the next mesh that I do, it should be off, but I'll make it off anyway. So support is this mesh. Okay. And do the same thing on this side. Notice that this has to be off. Yeah, this has to be off. It is off because otherwise it'll merge these two nodes and you don't get the you don't get duplicate nodes there mesh. Okay, very good. Now cross-sectional area. So we go to properties first, create a profile. It's going to be circular, 2.486. This circle of inches. So a circle of this size is going to give you an eye, bending eye, which I needed in the analytical solution of 30 inch to the 4. So that's where this number is coming from. So that's good. And now we're going to create the sections. We can do it at the same time, this guy and that guy. Make sure you change the profile 1, and then we say okay. Very good. Now we are pretty much done here, except that I will create a group at that location. Okay, so let me go and create a group. Now notice that this is the 10th element. Let's go and create a group, and it's going to be a manual group. I just want to create this node. Okay, this is going to be node number 11, I believe, but it's one node that I picked because I can put the load on this group, but I cannot put it at the particular node location. Okay, so that's fine. This group has been created here, right there. You can see that. I could have called this thing, for example, node concentrated location of the concentrated force, etc. But that's fine. Now, I don't need to do it at the end because the ends seem to be immune to it. Although, if you have any doubt, you can create a group here, left group, right group. You can call this thing middle group so that you know exactly what. But for these endpoints, you will see that I really don't need to create the group. Okay? You can do it, as I said, but it doesn't matter. Now, that's pretty much it. So now we're going to go to uh, structural scenario creation. Select the finite element model. Okay. Notice that procedure has to be defined. Procedure, because I'm trying to show you a very simple linear static problem. I'm going to do static perturbation instead of the static general. This is a linear problem, basically. Okay. Now for boundary conditions, this end is clamped. So I'm going to select the clamp. This end is clamped. Okay. This end is a roller, so I'm going to go to fixed displacement, select this point. It can roll in the direction y, it can move in the direction y translate, but it can rotate about x, but cannot rotate about y and z. That becomes a roller. And now for loads, notice that, let's do the force first. Now, notice that I cannot select any one of these, or even if I have the node there, I cannot do it, but I can go and put it on a group. See that? So for support, use the pull down menu, select the group. It tells you there is only one group that I have. You can put the load here. Okay, and it's downward minus 8,000 pounds, which is 0.8 kilopounds. Okay, so it's good. And also I have a torque or a moment at this end. Now I can put it at that point, no problem. Okay, and it's let me see now. It is clockwise. Okay, so minus about x minus 30,000 pound feet. You say okay. All right. Now, one thing I forgot to do, remember I had to create a connectors here. See that? Connectors. Where is that? Right there, connector. And that has to be done in the, not in the, while you're doing in the scenario creation, you go back to your model. I forgot to do that. So you go to the model or double click on this so that you go back to there. So I'll go to model. Oh, here is the connections tab. There's the connections tab. Scroll to the right. Here is the connector. And the connector is going to be between ends of these two lines. So to make my job easier, I'm going to hide one of these lines. Okay. Oops. Hide one of these lines. So for the first support, for example, this point, which is the end of that line, for the second one, I go to the hidden mode and I select this point, another vertex, okay? And then go back here. Now I don't want this thing to be beam, I want it to be a hinge right there. And notice that it asks you to pick the axis system. The axis system is in hiding. You can go there and select it. Let me get it from the table, from the tree. Let me get it from the tree. There. You can go there. Oh, not there. Access system. You can go there and pick it from here, or you can get it from the tree, whatever you want. So I'll get it from here. That's too hard. There, access system one, and then go back there. You update the mesh. You see that? This is X, and X is this way. If you have any doubts, bring this thing into show mode. X is going like that. Direction of hinge is X, and then say, okay, done. So we're pretty much done. Let's go back to the scenario. Find down the model. Where are we? We go here. Oh, all right. So now we go to the uh, simulate. First, let's check our stuff. Model and scenario creation. This is the model and scenario check. Good. So no error here. Let's check this one. I don't anticipate any error here. This one is the simulation check. And finally, we're going to run it. Run means simulate. After this is done successfully, you're going to simulate. And we're going to check the displacement, maximum displacement at the hinge. It should be your 4.58 inches downward. Okay, that's done. Here comes the moment of truth. Very fast calculation because this is just, it is done because it's just beam, bunch of beam elements. Okay, that's good. All right, so let me close this. Let me get the displacement. Let's look at the view from the front. Where is the view from the front? Front view, because it's a two-dimensional problem. From right there. There is the internal hinge. That's why you can see that the slope is changing, and in fact, you can see that 4.58. Now, to convince you that it doesn't matter whether I took a hinge or I took a join or I took a cylindrical, I go back to my engineering connection. Double click on the connector. Okay, I'm going to change this thing to join. Or let me yeah. Well, let me first try this. Let me try the cylindrical first. Cylindrical. So it's not a hinge anymore, but the axis system is again lined up. And this is where this page is going to help you. See, this is the axis of the cylinder, which is direction 1. Okay. So let's go back here. So now it's a cylindrical joint. We're going to run it. So let's go to scenario and run it. Simulate. We should get same number, 4.58. and then I'm going to change that thing to join. Join? Yeah, join right there. So the next 5 videos are going to be variations of choosing different things to do the same problem. And let me close that. 4.58. Let me go back, change. Let me go and change this thing to join. Now, join, you cannot find it there. You have to change this thing first of all to uh, to let me see, specify, specify, and then change this thing to join. So that is what this slide is. Where is that? That is what this slide is about. Specify, select join. And again, it requires an access system, which is the correct one. You say okay, and now run it. Scenario, simulate. Okay, you should get the same number. But in the future videos, I will only use the hinge. Okay, I will not use the other options. Okay, there's no reason to do that. But I will keep telling you that, hey, I've done this thing in tutorial 10. If you have any doubts, please check there. Okay, so let's say 4.58. All right, folks.